Lecture 5, Part 1. Interactions between EM energy and surfaces. Interactions between EM energy and surfaces. 1. As mentioned in a previous chapter, the radiance L is the most important of the physical quantities in remote sensing, because in fact it is the primary measurement quantity of the interaction processes between electromagnetic energy and surfaces. The whole process of interaction with surfaces follows the principle of conservation of energy expressed by the Kirchhoff relation, whereby P plus alpha plus tau equals 1. Where P, alpha, and tau are the reflection, absorption and transmission coefficients respectively, which represent the fractions of reflected, absorbed and transmitted energy with respect to that incident. Interactions between EM energy and surfaces. 2. It is evident that, for opaque bodies in certain spectral intervals, and this happens for the most part of our sensitive experience, the value of tau is 0, or in any case negligible, so the components of the balance are reduced to that of reflected energy P and absorbed alpha. Recalling that the energy absorbed serves to thermally charge the body in question and then trigger the phenomenon of the emission of electromagnetic energy, regulated in turn by the emission coefficient, the radiant flow coming from a generic surface substantially includes the contribution of two components, that of the reflected energy and that of the energy emitted. Radiation's geometry. 1. Geometry of the radiation is the descriptive study of the position relations of the source and the sensor with respect to the observed surfaces, as shown in the following figure. The scheme shows two radiant flows, one incident phi and the other outgoing phi, affecting a point Q, or an elementary area dA, belonging to the generic surface S from which two symbolic cones branch out which enclose the radiance subtended to the inside of their respective solid corners. Radiation's geometry. 2. A reference symbology is used to distinguish the two conditions of incident and outgoing radiation. By convention, the angles with respect to the normal n, zenith, and to the direction d, azimuth, are indicated by theta, phi if referring to the source, incident flow, and with theta, phi, respectively when referring to the direction of observation, outgoing flow. Similarly, the radiometric quantities observed, in the cases of possible confusion of terms, will be distinguished from those incidents for a first apical, with the exception of those that are distinguished by their own definition, such as irradiance E and excitance M. Radiation's geometry. 3. From the physical point of view, the surfaces involved in the radiative transfer phenomena have a variable behavior, in the sense that they do not always maintain the same characteristics in all the directions of observation. Indeed, natural surfaces generally behave in an anisotropic manner, i.e. they direct not uniformly the radiance in different directions depending on their structure and geometry. Sometimes, however, in conditions very close to the ideal ones, they can be assimilated to isotropic surfaces, so that the radiance is distributed uniformly in space. It is useful to remember some reference models, among the many possible ones, that allow to simulate in a simplified way the real situations, as in the following schemes. In relation to the portion of space considered, directional, conical or hemispherical propagation can be mentioned, depending on whether the radiation affects a simple direction, a solid angle or a half-space respectively. Specular and Lambertian surface. 1. Specular surface is defined as a surface whose observed radiance value L, theta, phi, is reflected in one specific direction, angle R where R equals I. Lambertian surface is defined as a surface whose observed radiance value L, theta, phi, is constant for any combination of geometry between the source, theta, phi, and the observation point, theta, phi. This surface takes on the meaning of integral diffuser and, like the black body, it is only an ideal model. A good approximation of specular surface can be a mirror, while for a Lambertian surface can be, for example, the screen of the cinema, constructed in such a way as to reflect the light in almost the same way in all directions, so that from any position the spectators can see the projection at best. Natural surfaces, although sometimes approaching this model, generally exhibit more complex behavior. In the following slide, specular and Lambertian surfaces. Specular and Lambertian surface. 3. In the case of a perfect diffuser, the observed radiant intensity 1, theta, phi, depends only on the incident radiant intensity according to the normal I, theta equals 0, phi, and on the cosine of the angle of view theta with respect to normal n. Essentially, the radiant intensity value at output I, theta, phi, decreases in a linear mode with the increasing of theta according to the following relation, called cosine law or Lambert's law. Specular and Lambertian surface, 4. In order to verify the trend of the radiance L, theta, phi, with the variation of the observation position, being. This last relation shows how, in the case of surfaces or means with Lambertian behavior, the observed radiance L, theta, phi, no longer depends on the observation geometry, but simply on the intensity of radiant flux according to the normal I, O, phi, and the extent of the area involved A. Directional radiant flux conditions, 1. In the case of a radiant flux coming from an infinite distance, or in any case from far away with respect to the dimensions of the interested areas such as, for example, from the Sun to the Earth, the radiant flux can be represented by a set of parallel rays. Directional radiant flux conditions, 2. In these cases, the angle of exposure theta of the affected surface dA, defined by the normal n to the surface and the direction of the incident flow d, is very important. In fact, for conditions of theta not equal to 0, for simple considerations of the projective type, the surface dA will always be greater than that normally exposed dA of an inverse factor to cos, while the latter, vice versa, reduced by a factor cos. By definition, EO irradiance is expressed by the relation, where the index 0 indicates the angle value theta equals 0 in the normal condition. Directional radiant flux conditions, 3. For any other surface dA oriented differently from dA, the relation is, considering that the irradiance for a generically oriented surface is given by replacing, we will have that, which allows to calculate E when EO and the exposure angle theta are known. Conical radiant flux conditions coming from a point source, 1. Given a point-like electromagnetic energy source Q, e.g. the Sun, which radiates in space with intensity 1, to define the irradiance value E that affects a generic surface D located at a distance R from the source. Conical radiant flux conditions coming from a point source, 2. By definition, the radiant flux intensity is where D is the solid angle subtended in Q by the surface dA perpendicular to the direction of the flow, expressing the value of the solid angle D according to the area dA. Conical radiant flux conditions coming from a point source, 3. Thus, by replacing in the initial intensity relationship, where theta is the angle between the normal n to the surface dA and the direction of the radiant flux d. Finally, by expressing the last report in terms of irradiance E. Conical radiant flux conditions coming from a point source, 4. It results that the irradiance E coming from a point source towards a generic surface dA is proportional to the value of the radiant intensity 1 to the source and to the cosine of the angle theta between the normal to the surface and the direction of the radiant flux d. This concept is known as the law of the cosine of irradiance. Moreover, irradiance E is inversely proportional to the square of the distance r from the point of source Q. This fact is also expressed as the law of the inverse of the square of the distance. This law is valid for point sources, which are difficult to implement in practice. The assimilation to the scheme is valid, with an error contained within the limits of 1%, when the source Q is placed at a distance r at least 5 times greater than the physical dimension of the source as observable from any point belonging to the surface dA. Conical radiant flux conditions in the hemispherical space, 1. Finally, consider the propagation of electromagnetic energy in space considering a hemispheric model, as in the case of Lambertian surfaces. In this case the m, or the irradiance E, recalling the definition of radiance L, can be expressed as follows. In geometric terms, the solid angle d that subtends the elementary area dA, affected by the radiant flux coming from a point Q, or incident on it in the case of an incident flux, can be expressed using a function of the angles theta, phi as in the diagram of the following figure. Proof of Kirchhoff's theorem, 1. Remembering that, given a real homogeneous anisothermal surface, its spectral and directional emissivity coefficient, theta, phi, is defined as the ratio between the real radiance emitted and that which would be emitted by a blackbody surface placed at the same kinematic temperature T, theta, phi, according to the relation. Proof of Kirchhoff's theorem, 2. Two infinitesimal surfaces, dA and dA, are placed in a radiant cavity, respectively being a black body and a gray body. These surfaces form angles theta and theta between the normals to the surfaces themselves and to the joining of their centers of gravity r, following figure. Proof of Kirchhoff's theorem, 3. In isothermal conditions the radiative flux exchanged between the two surfaces must be in equilibrium. Then calculating the radiant flux from dA to dA, we have proof of Kirchhoff's theorem, 4. Whereas, however, the gray body surface dA also reflects the radiant flux coming from the black body surface dA towards dA itself, remembering the principle of conservation of energy for opaque surfaces, i.e. alpha plus rho equals 1 and then rho equals 1 alpha. dA reflected energy quantity will be proof of Kirchhoff's theorem, 5. In the following two slides it can be verified that alpha equals proof of Kirchhoff's theorem, 7. This equality allows us to better understand Planck's law, which originally formulated only for black bodies, can also be extended for gray bodies considering 1. The principle of energy conservation, generalized for opaque bodies, turns out to be rho plus equals 1. A very emissive surface will therefore be little reflective and vice versa. It should be noted, however, that this principle applies only to isothermal conditions and therefore not in the real case of acquisition with multispectral sensors. Specular and diffuse reflection, 1. The phenomenon of reflection is governed by the physical characteristics of the surfaces involved so that there is a double behavior, as previously anticipated, specular, in the case of very smooth surfaces, and Lambertian, diffuse, in the case of surfaces with a certain roughness. In both cases, the outgoing radiance will be regulated by the anisotropic and isotropic models, respectively. Specular and diffuse reflection, 2. The separation between smooth and rough surfaces depends on the scale of analysis. Indeed, a good criterion of distinction can be that of Rayleigh, according to which the limit of smooth surfaces is defined by the relation where h is the height of the discontinuity of the surface, lambda the wavelength and theta is the angle of incidence. Specular and diffuse reflection, 3. More generally, we can say that, if the discontinuities show h lambda, the surface can be considered rough and therefore there is a diffuse reflection, Lambertian surface, while in the opposite case, when h lambda, the surface appears smooth and there is a reflection of specular type, mirror. Evidently a surface can take on different aspects as a function of lambda. For example, a desert sand may appear rough due to short wavelengths, in the visible or near infrared, and be smooth in the microwave region. Obviously, the reality that surrounds us is mostly composed of surfaces that behave in a composite mode, without the clear prevalence of one of the two types of reflection, so that the final result, in addition to including mixed situations, produces anisotropic reflectances, that is variable according to the direction. Specular and diffuse reflection, 4. In the case of acquisitions made with multispectral sensors placed on board satellite platforms, which orbit at altitudes higher than 400 km, if we consider the wavelengths of the visible and infrared, h is always greater of lambda, so all the surfaces are to be considered rough and therefore Lambertian. This ensures that the sensor always receives a fraction of reflected radiant flux and that therefore the failure to record this flux is characteristic of surfaces framed with alpha equals 1 black bodies for such wavelengths, in the hypothesis of opaque surfaces. Specular and diffuse reflection, 5. This last statement, given the variability of ρ with respect to wavelengths, does not apply to all incident S. Especially for long wavelengths, microwaves, surfaces that are opaque in the visible and infrared, they can become smooth and therefore behave like specular reflectors. This means that the sensor may not record some component reflected due to the divergence between the position of the sensor itself and the angle of reflection of the mirror surface. In such cases, therefore, the absence of reflected flux recorded by the sensor could mean both a surface with alpha equals 1 and a surface with ρ0 which however reflects in a direction diverging from the sensor.